This is another good question. Example 25. It's from Verma, chapter electricity. And we have to find the equivalent resistance between A and B. So one thing that you would see is, first of all, this thing is completely symmetric. If you consider a horizontal line going across, it's completely symmetric. It's 5, 10, 5, 10, 5, 5, 2.5, 2.5. And so you can reverse the polarity and the distribution of the currents would be same. Like you can have a battery connected just for just for like as a mental model. And you if you have, let's say, let's just talk about this thing inside, because it kind of resembles a Wheatstone bridge, except that we have a lot of resistors inside. But see, you can completely see that those it's completely symmetrical. So the current that's entering here and the current that's entering here, and then let's say it's the current that's entering here is some I, and then we reverse the polarity, and because of the symmetric reasons, the same current I should enter from here. Now, if we again uh, change the polarity, changing the polarity doesn't change the distribution of the current, it just changes the direction. So we change the polarity yet again. And so this I current is now entering. Here the current I1, there should be I1 current here. It was entering if we reverse the polarity. So it should exit when we again reverse the polarity, not I1. I current should go outside. Well, if we change the polarity, because changing the polarity doesn't change the distribution of current in such cases, it just changes the distribution. And not this, sorry, it doesn't change the distribution, it just changes the direction. Direction of I has changed, it's going out. So you can see in these two wires, there's the same current. I current and this I current going in and the I current is going out. So there is no interchange of currents between this wire and this horizontal wire. There is no change. I would say an interchange and intermixing of current between these two wires. So this the same current, no current is being gained in this vertical wire from this horizontal wire, no current is being lost. So, though in the question they have, of course, said that these wires are joined together, but since the current is not interchanging, since the current is not mixing between these two wires, we can say the same would happen if the wires were physically different. If these two wires, if let's say I'm talking about this wire, if this wire and this wires were physically different, were physically not joined, then also the same would have happened. Similarly, the current would have not have interchanged, and now also the current is not being interchanged. Of course, you cannot apply this argument. Now, I guess you can only apply this argument when you have symmetry, and you can derive in some other way that the current is not getting intermixed. Here, it's not getting. So we can say we can take the wires as physically different, and nothing would change, right? So as nothing is changing, first of all, we can take these wires as physically different. So let's just write a bump here. Let's just have a bump, right? So for this wire, the equivalent resistance is just 2.5 plus 2.5, and that's 5 ohms. And for this wire, it's 5 plus 5, that's 10 ohms. Hence, you can take this wire completely out. Let's just disconnect this battery, this mental battery. Can take this 5 ohm wire outside so that it looks kind of neat. Mhm. This eraser is too big for the figure. No, uh, it's just this, and this can also be simplified into just a 10 ohm wire. So it's just a 10 ohm wire now. These are the remains. And we have taken this thing, taken the vertical thing outside, and oh, it's a 5 ohm wire now. This is a 5 ohm wire now. Now it's a bit easy to calculate the equivalent resistance between points A and this point B. How you ask? Well, we can uh just calculate the equivalent resistance of this part. And since this part is in parallel with this 5 ohm, just hear me out. Since this part, not this part is in parallel with this 5 ohm, we can use the parallel formula. So just need to calculate the resistance of this part inside. If you don't understand how are we using this formula for parallel resistance, you can say, of course, it's kind of a Wheatstone bridge configuration. So what you can do is you can rearrange it. You can add or subtract and using a scissor, you can manipulate the wires. So the whole thing becomes, we have A here, we have a 10 ohm and uh 5 ohm. Wait, oh, it's a 10 ohm and a 5 ohm, right? Okay, we used to connect it this way. It's not a Wheatstone configuration, sorry. I took the 5 ohm wire outside, and now it's not a Wheatstone. We can still calculate the resistance and have it in parallel with this 5 ohm. But a better way, what I do would be is to take the 10 ohm wire outside, because then it gets a Wheatstone bridge configuration. It gets Wheatstone bridge configuration. So we can have this 5 ohm wire inside, and that's how we could not convert it into a Wheatstone bridge. Of course, it's not a balanced bridge, but anyways, and you can take this wire outside now, this horizontal wire outside, and now you have a Wheatstone bridge. Sorry, there was a little confusion between if there was horizontal or vertical. Now you have a Wheatstone bridge configuration, which is in parallel with this resistance. But if you do not see how is it is in parallel with this configuration, you can convert it by adding or subtracting wires into this form. A, and we have a 10 ohm and a 5 ohm resistor. This is point B, a 5 ohm and a 10 ohm. So again point B. And in between we have a 5 ohm resistor. This is 10, this is 5, this is 5, this is 10 ohm. So it's completely equivalent. As you can see here, this thing is completely equivalent to this. And plus, we have added another 10 ohm resistor. Another 10 ohm resistor. So you can just calculate the equivalent resistance of this wire and have it in parallel with this 10. Right. I think I did quite a bit wrong things in the previous assumption. Right. Now it's just easy to calculate. It's not very easy. I mean, if you are used to it, you can calculate the resistance. There's no bit fixed formula as per HC Verma. I think there are some kind of equations that people use, but I'm not aware of them. So let's say and there's let's just ignore this 10 for y for a minute and just calculate the equivalent resistance. So let's just ignore this wire for a second. Let's just cut it. And let's say an I current enters. So this I current enters gets divided into an it's just it gets divided into this I1. It's just for it's not it's just a mental image. It's not what really happens if you do connect the wires. It's just for calculating the equivalent resistance, right? An I1 current goes from to this side and an I minus I1 current goes this side. And then and I minus I1 current enters by symmetry. If you can, so you can change the polarity. You can the same argument I used like 2 minutes before, and an I1 current goes. Now that means something might have, if it was initially I1, something might, if we assume something has gone, not something has reached, if we assume some current has gone, then that gone current, let's say it's X minus X must equal to I minus I1 by the junction law. So X is 2I1 minus I, X is 2I1 minus I, right? It's 2 I1 minus I. It's we have assumed it's going out. So it's in this direction. Now we can write the potential difference between these points A and B. So one way is we can go through this configuration, and another is we can go through this. We are not going through this because it's mathematically equivalent to going through this, and we are not, of course, going through this because it's mathematically equivalent. No, it's not mathematically equivalent to going through this, but the point of symmetry has already been used because we are using this I1 and this I minus I1 here. So it's of course the point that it's symmetrical, that there's a 10 and 5 ohm present here has already been used, because if the 10 and 5 are not present here, then this current will not be I and this should not be I minus I1. So we are using this point, though not directly, just you may think that okay, you are going through this and you're going through this, so you're completely ignoring this 5 ohm. We can't relate it. No, we cannot. Because of this 5 ohm only, you have an I minus I1 and I minus I1 here and an I1 here. If this 5 ohm was not present, then you would not have used. So you just need two paths to go. First, you go through this path, and so you get delta A and B. That's the delta V as 10I IR, or okay, just 10I plus 5I minus 5I1. I use the distributive property. So it becomes 5I1 plus 5I. And the second way is we can go through this path. So it becomes 10I1 plus 5 to that 10I1 again minus 5I, 10I1 minus 5I, and finally it reduces to 10I1, which becomes 30I1 minus 5I. And since these two are equivalent, and you just need to calculate delta V by I, or delta V by I, you need to convert the whole thing in this I1 in terms of I. That can be done by substitution. So you equate both of them. So 10I, no, sorry. Okay. So 10I becomes 25I1. So I1 is 2 by 5I. I1 is 2 by 5I, right? We can't substitute here. I, I, I1 is 2 by 5I, and this whole thing becomes 7I. 7 ohm, I'll rather like to say. And so we divide delta V by the current that we sent. That was I. So 7I by I. So 7 ohm is the equivalent resistance. Now let's join it. Of course, the current will go differently. Let's just delete this thing. Okay, so now we have a 7 ohm resistor here. We have a 7 ohm resistor here connected in parallel, to this 10 ohm resistor, and with the formula 70 by 17 becomes equivalent resistance, which is 4R is 68, and 20 is 1, and 30 is again 1, and 130 is 119, which is 7R, and yeah, 4.1 is the answer given, which is all right. So that was it, and this is the answer. Bye.